Hello, welcome to this video, and in this video we shall be looking at the product rule and the quotient rule. And before we get into those, we'd like to first look at differentiation of a few more algebraic expressions. Now, I already saw that the derivative of x to the power n is n times x to the power n minus 1. So we know that the derivative of x squared is simply 2x. The 2 comes down and the power reduces by 1. The derivative of x to the power 4 would be 4x cubed. The 4 comes down, the power reduces by 1. How about expressions like 2x squared or x cubed plus 2x? How would we get the derivatives of those functions? Now, that operator d dx is a linear operation. Because of that, this is the same as 2 times the derivative of x squared. So this would be 2 times 2x, which gives us 4x. And this would simply be the derivative of x cubed plus the derivative of 2x. But you also know that the derivative of 2x can be written as twice as the derivative of x itself. So this would give you 3x squared plus 2x when you carry out that rule right there. Okay, how about the derivative of a constant function? Say the derivative of 5. Now we know that 5 can be written as 5x to the power 0. And so you can see the derivative of this would be 0 if the power becomes a multiplier. So this should all be in mind while you're carrying out differentiation of more complex algebraic expressions. Now let's get into the rules. We'll start with the product rule. So say we have a function y, which can be expressed as two separate functions of x, u and v. So we have y is equal to u times v. We let delta x be the small change in x. That would cause u to change by delta u, v to change by delta v, and y to change by delta y. So all u is a function of x, v is a function of x, and therefore y is also a function of x. So what we have here is that y plus delta y would be equal to u plus delta u times v plus delta v. But remember, we want delta y out of delta x. So we can take the y to the right. This would be u plus delta u times v plus delta v minus y, which is u plus delta u times v plus delta v minus uv. Now we can expand the right-hand side such that we have uv plus u delta v plus v delta u minus delta u delta v, plus delta u delta v minus uv. And this leaves us with u delta v plus v delta u plus delta u delta v. Now what do we want? We want delta y out of delta x. So we can simply just divide all through by delta x. Delta y out of delta x would be equal to u times delta v out of delta x plus v times delta u out of delta x plus delta u delta v out of delta x. What's the next step from here? We know that as q moves closer to p, which is as delta x tends to 0, the expression delta y out of delta x tends to the gradient of the tangent at that point, which is dy dx. And so Allow me to write that here. dy dx would be equal to u times delta v out of delta x. But what else changes? We know that as x tends to 0, delta v out of delta x also tends to dv dx, and delta u out of delta x should also tend to du dx. So what do we have? We have that dy dx would be u dv dx plus v du dx plus what now? Now delta u, delta v, because as delta x tends to 0, delta x being so small, delta u and delta v would also tend to 0. And now a product of a small number and a really small number makes a really, really small number. So even if you decided to, put out delta v out of delta x, and you made this tend to the vdx, you'd still be multiplying it by a really small number. So this product would tend to 0. And therefore, this would be your expression for the gradient function of the product. Okay. Now, how about for the quotient rule? Say we have a function of x, y, which can be expressed as two separate functions of x, u, that this time divide by v. Would go with the same letting, yeah? Let delta x be the small change in x that would cause u to be small change in u. I'll just have that there. So we have the delta u, the delta v, and the delta y, the same exact expression. So that would tell us that y plus delta y is equal to u plus delta u divided by v plus delta v. So delta y would be u plus delta u out of v plus delta v minus u out of v. Or if we subtract y from both sides, what we know that our y is just u out of v. If we try to make this a single fraction, we'd have v plus delta v times v in the denominator, and then u plus delta u times v minus u times v plus delta v. Then in the numerator, this is uv plus v delta u minus u delta v minus uv out of v times v plus delta v. And this is equal to v delta u minus u delta v out of v times v plus delta v. But what do we want? We want delta y out of delta x. So if we divide both sides by delta x, strategically, we divide the terms only in the numerator by delta x, because that would be the exact same thing. So we'd have v times delta u divided by delta x minus u times delta v divided by delta x out of the same denominator v times v plus delta v. We know that as delta x tends to 0, delta u out of delta x will tend to du dx. Delta v out of delta x will tend to dv dx. Delta y out of delta x will tend to dy dx, and delta v will tend to 0. This delta v is this one in the denominator here. Yeah. And so, because of that, dy dx will be equal to v du dx minus u dv dx, but out of v squared, since our delta v is tending to 0. And this would be the expression for the gradient function of the product u out of v. Okay, these rules that we're going to use a lot, so let's look at a few examples. For us to differentiate x plus 4 out of x cubed minus 2x with respect to x, we could let y be equal to this function here. x plus 4 out of x cubed minus 2x. Then how would we go about it? We know that dy dx for product is equal to, if our product is u out of v, dy dx is going to be v du dx minus u dv dx out of v squared. So what's our v? Our v is x cubed minus 2x. So we'll have this as x cubed minus 2x times du dx. Du dx is the derivative of the numerator, and you can see the derivative of the numerator is 1. Because when you differentiate x, you get 1. When you differentiate 4, which is a constant, you get 0. So minus u dv dx. So u times the derivative of the denominator, and you can see the derivative of the denominator is 3x squared minus 2. All this out of v squared is x cubed minus 2x all squared. The rest is really just algebra. This is x cubed minus 2x minus x plus 4 times 3x squared minus 2. So you have your x minus 3x squared, which is minus 3x cubed, plus 2x minus 12x squared, and then plus 8. All this out of x cubed minus 2x all squared. What does this give you? You have a minus 2x cubed minus 12x squared and plus 8 out of x cubed minus 2x all squared. You could factor out the 2, the numerator, or negative 2 if you like. So this is x cubed plus 6x squared minus 4 out of x cubed minus 2x all squared. And that would be your derivative of that function. So you'll have differentiated that function with respect to x. How about a product? Yeah. So if our function is this, we can let y be equal to this function, which is x squared plus 4x plus 1 times 6x to the power 5 minus 10. We know that if y is equal to uv, then dy dx is equal to u dv dx plus v du dx. So we could start with having our u times dv dx. So the derivative of the other function, you can see this is going to be 30, because the 5 is going to multiply by coming down. 30 times x to the power 4. When you differentiate 10, you get 0. Plus v du dx. So 6x to the power 5 minus 10 times the derivative of the other function, which is 2x plus 4. And then you can expand that, and then you get your answer. So that's simply how we use the product rule and the quotient rule in differentiation.